Good morning, everyone. We're at Team 6. Our project is the Fresnel lens water purification system. My name is Maria Ramayo. This is Obama Watt and Gerrit Lopez. This is the outline of our presentation. We'll start with the product statement, the objectives, we'll extract the design, the components, and then with the different analysis, and then we'll conclude with the conclusion. So, according to the World Health Organization, 750 million people do not have access to clean water, and they spend around 140 million hours during the day collecting water. And approximately 2,300 people die every day due in part to inadequate drinking water. Since solar and wind energy are readily available, they're free, they're natural, and they're more friendly environmentally resources, we wanna base our project only on those resources to find a solution for a worldwide problem, which is contaminated water. Our objectives. With this project, we look to solve a solution for a human necessity, which is clean water. Around the world, there are some communities, especially in developing countries, which they do not have access to clean water. And we want to create this affordable unit which can be employed in those developing countries. And we only want to use renewable resources, which is wind energy and solar energy.
Now, this is a general overview of what our system will do. We have a large particle filter. It will be made of natural materials. The water will be then fed into an unprocessed water reservoir and then gravity fed into a specially made boiler. This boiler will be heated by the Fresnel lens, and once the water boils and evaporates, it will be channeled into a condenser, it will be cooled, and then stored into a water reservoir for drinking or any useful purposes that you might need. We'll also have a sediment collector just in case you need to flush out the system and get rid of all the dirt and all. Now, this is one of our proposed designs we made. As you can see, the filter, the unprocessed water reservoir, the boiler, the lens, the condenser, and the storage tank. The lens we're using is about 36 by 27 inches. It's a linear type lens. Focal point is 26 inches, and according to the manufacturer, you can get anywhere between 590 to 1,040 degrees Fahrenheit at the focal point. There's about 4.5 hours a day of sunlight in Miami, and with this, we expected to produce at least 11 gallons just with this. Now, these are the major components of our system. The lens itself. The reason why we chose a Fresnel lens over a regular lens is, as you can see, the Fresnel lens is designed with ridges and it better focuses the point of sunlight than a magnifying glass. The lens is also cheaper to produce. It's made out of plastic, not glass, and it's very lightweight. We also try to attach a solar tracker to our lens itself, so it's able to track the sun's position throughout the day. The tracker will be attached to linear motors, so the focal point is always maintained, and you can have optimal volume times. Now, continue with the components. The filter. The reason why we have a natural filter is made of gravel, sand, charcoal, cheesecloth. This is to get rid of like rocks, twigs, leaves, anything like that. Like when you pour in the dirty water before it goes into the tank, the first unprocessed water reservoir tank. The boiler must have minimum design specifications. It must be able to at least heat up to 212 degrees Fahrenheit, have high thermal conductivity, not release any chemicals when heated, and be corrosion resistant. Some materials we're thinking about for the boiler itself should be glass, copper, cast iron, aluminum, or high temperature ceramic. We also have a condenser, basically similar to like a radiator. It will be made of copper tubing and aluminum. We'll make it long enough just in case there's not enough wind. It has time to cool before it's stored into the reservoirs. And the reservoirs basically, both reservoirs will basically be 2 5-gallon tanks.
Okay, so some of the challenges we have, obviously, is make it low cost. That way we can employ it in like different parts of the world where like there's not many resources. We're aiming for $300 or less for the whole system. We also want to make sure it's reliable and safe to operate. We don't want any like kids or like the user or wildlife to like get injured during the use. We need to make sure it's low maintenance and easy to maintain. So basically all the parts are detachable so you can clean them. Also, we want to make sure that it's an efficient system. We don't want to make sure like we don't get like just like a cup or two of water because that would be useless. And obviously maintain a constant flow rate throughout the whole system. Some of the analysis we're gonna conduct on this are thermal conductivity, mainly on the boiler, to make sure that it spreads the heat evenly. The thermal stress, since this is gonna be like heated up and cooled down every day, we're gonna make sure the parts don't fail. And fluid mechanics, in order to maintain a constant flow rate throughout the whole system. And as I mentioned before, safety and the cost material. Also, water quality is probably one of the most important because when you boil the water, like all minerals and things like that get left behind. So we need to remineralize the water so it's good for you and safe. What about the lifestyle? There's a lot of other products out there that are, for cleaning water. Basically, they're just filters and they're meant to be used like as a personal thing. And so it's a completely different product. Our product is supposed to like get you water, even to shower and things like that, wash dishes or whatever other needs you may have. It's also cheaper and long lasting. Well, I mean, the first investment, will be a lot higher, but the lifestyle is about $20 per piece. It gives you about 1,000 liters. So eventually, you're gonna have to get a lot of them. Also, like our system is less likely to clog. This, if your water is really like murky and stuff, eventually it will clog. And also with our system, after we optimize it, we're hoping we can also clean, like desalinate water, which is like a very expensive process.
So these are the standards that we want to use and follow. The first one is solar energy, and then we follow with the energy and quality management. We want to ensure that our project follows these standards so we have a good performance and it's efficient. And we have the water heating systems, the guide to pick the materials. This is going to help us to pick the best materials for a water heating system using solar energy. And the next one is for the copper tubing coils. We're going to use copper tube for the coil, for the boiler, and for the condenser. So we want to follow this standard as well. These are the division of responsibilities.
Oh,
and
that was fast.
there you go.
They were fast. I thought we were ahead of schedule.
We want to try to split the work in an equal way and to get same experience and work together as a team. And as our conclusion, we're going to use the Fresnel lens to purify water using solar energy and give a solution to a worldwide problem. And this is the future work. We're going to work on the solar tracker. Hopefully we get to water salination and self-clean.
Any questions?
Thank you for your time and open the floor for questions.
Oh, of course I have a question. Now, obviously this will work with salt water as well because it's actually evaporating, so you don't have to worry about that. But everything's going to be gravity fed here?
Yes.
No pumps, nothing?
No pumps.
Now, having a plastic lens, are you concerned about durability with that, getting opaque or anything over time?
Yeah, of course. I guess we will have to have like some sort of replacement, but they're relatively cheap.
Also, you don't want a kid going under the lens and frying themselves with that.
We plan to build a safety net around the lens so you can't interact with the actual boiling apparatus out there. Also, you could cover the lens when not in use or something like that.
Now, how are you planning to remineralize the water?
There's a lot of things like powders, basically, like hydrogen, and basically just like throw it in the water.
So you actually have to go to the store and buy minerals?
We will have to supply it with the system, basically. There's really no other way.
Well, I'm thinking no minerals is better than bacteria in your water, but water is water. The minerals, they could chew a rock. I mean, what you want to be concerned if you don't want to use anything that you filter to put back in there because you're gonna have a problem. But did you say how much water you would get?
Yes.
11 gallons.
Sorry, I missed. 11 gallons.
And just to add
Right.
to the remineralization,
Yeah, that's good.
you can drink distilled water. It's just that it lacks certain benefits over mineralized water. There's no harm in drinking.
It's like Dasani.
Right.
It has no flavor.
There's no harm in drinking distilled water.
No, that's a a good idea. What about mirrors? Do you think about it? There's a pretty cool idea that I was looking at because they use it for power plants, solar power plants, where you have a convex mirror,
Yes.
very shiny, pulling right on a pipe, and then you can have
that.
water
That's one
flow.
of our design
That's one of our
alternatives,
design.
but, we were talking with one of our advisors, and he basically said it wasn't a good idea, it's just not efficient.
Well, if you don't have any pumps, that's a problem.
Yeah.
But if you have pumps, that would be great because you could get a pretty high flow rate going through there, and you get steam out of the other end. I mean, and
The
the
reason
industry.
we chose this over that was basically because this will be more efficient.
Sure,
So-
And again, we want it to be completely solar powered. No
Okay.
pump, just,
that makes sense.
just sun doing all the work.
Now, will that track the sun?
Yes.
Yeah.
Yeah, it's got a tracker.
Yeah, we're gonna put a
That's why
tracker.
you saw the sensor that I saw
Yes,
on
the
the
sensor is gonna be a 2-axis type of sensor, so it can both lean forward and actually tilt left or right to maintain the
To keep up
optimal
with the solar position.
position. So the sun position, because it changes throughout the day and throughout the year. And
And is that electric?
yes,
Yeah,
the
we'll
solar
have to have
tracker,
solar panels for that.
yes,
Ah.
a small solar, a really small solar panel because it uses really low wattage.
Okay, you got a start of everything, that's pretty
Yeah,
good.
the actuators will be actual used drills and it will be powered by the batteries. This won't use a lot of power since the tracking is incrementally done throughout the day. It's not a continuous thing. It does it, waits on minutes, couple hours, and it does it again. The sun position doesn't change rapidly throughout the day. So it's really low power, and I plan to use the drill backbones.
Now, one concern is, where's the source water coming from? You said,
Right. Any dirty water you can process, whether it's from a river, from a lake.
so you will have like a storage tank for that water? You come with buckets, fill that up, and then
Right, yeah,
have
you
it go
can fill it up, right. That's why we have the large particle filter to begin, just made out of natural material.
Oh, that's a
So
great
to get
idea.
rid of all the rocks, the gravel, all that stuff, and then the dirty water is in the next tank, and then that flows throughout the system. And that will be controlled by a valve before it gets to the water, so you can let in how much. That's how we're going to control the flow rate, and how fast it is heated, and how quickly you can make it go through the entire system.
Now, let's go back to the, about it being efficient. How efficient do you expect your system to be compared to other water purification system? I mean,
Compared to one of our other designs, this would basically get us at least double the water. Like what he was saying before with the mirrors, according to our professor, like that would just not get us anywhere near 11 gallons per day. Perhaps like 2 or 3, which is clearly not as good as 11. So.
And as you can see, the heating of the lens is very, why we chose the lens over other materials. It's really hot, and it's all ensure that it's going to be really safe. So if we can even get the medium 590 water boils at 212, we think we can create a really efficient system.
And what temperature does your lid melt at?
Really? That's where we're looking into the materials. The boiler won't exactly look like this for design purposes, but I'm thinking like a tankless water coil in heaters. So it'd be like a coil, so the lens will hit the coil linearly and it will heat the water as it circulates through that coil and then distill it, evaporate it at one end. The materials I'm looking to so far, I looked into one material in specific, type K copper. The maximum temp it could withstand was 400 degrees Fahrenheit.
Yeah, but you have 1,000 at one point.
Right.
That'll melt a lot. Well, the metal.
Well, the melting
adds
point
per
of
color.
copper is like 2,000. We're still looking into the materials. That's why we said possible materials. And I'm saying this is one thing we've been researching. So
And always when you have like a boiler, like you gotta have a safety valve or something, right?
right, yes,
Okay.
Pressure release
yes,
valve.
yes, definitely.
What potable water quality standards are you going to comply with?
Okay. We're still researching in more standards, and we're also planning get a mentor from the biology department and the civil engineering department, so we know what to take in consideration for the quality of water.
Well, I would suggest you add another bullet point there, certainly from a global perspective, that there are appropriate potable water quality standards that would be that you would comply with, just so you cover that base, because that's a critical component.
Yeah, definitely. Okay. Thank you.
let's go back to the economic part of this. Okay. You expect to have this system to cost less than $20, is what you're saying, right? Now, what's it going to cost you to do this project? What's the economic cost for you to do this project?
Without accounting for our time or anything like that, just materials,
Mhm.
that is about that $300. That's what we're aiming for. So, and obviously, since that's like the first one, it's gonna be like the most expensive, we do decide to like do this for like actually implementing it in like parts of the world or whatever, then the cost will go down from there.
So the prototyping, the time invested is longer than when you have a process down and you can make multiple units. Because we're still, this is new to us, and we definitely going to, so we're trying our best, and so we're trying.
And we're going to be trying different materials too.
Yeah, we did
So
a lot of experimentation.
We're going to be spending maybe, you know.
That's going to cost you $300? Is that what you say?
Well,
You guys are very optimistic. I appreciate that.
yeah, $300. You can't get anything for a tan for $300.
$300.
Now, I got a suggestion. I mean, do you know the lifespan of this device? And then you could calculate how much per gallon your thing's going to cost, right? I mean, you got to. What I like to see, for example, is your end result. What is the cost per gallon for the lifespan of the device? Is it a penny per gallon or something like that? You know, I know you don't have that yet, but I mean, think about that and look into it, because there's certainly a lifespan on that device. And then you can calculate how many gallons you get, and then you can get a cost analysis on how much per gallon. And that would be interesting to see how much it would cost to produce that water.
I have one final question. Have you got a slide on the division of labor in your team? Let me take a look at that again, please.
The one I had whiplash on.
Okay.
I'm up. We had a presentation in front of you talking about 70 gallons
Yes.
a day. We now have 11. Talk to me about what that does for me if I'm not in the U.S. and taking a 20-minute shower.
Well, I can. They said 70 gallons an hour, but the cost to us, the cost of that system would be relatively expensive, depending on solar panels and to drive it.
Let me rephrase my question. Your output is 11 gallons a day, yes?
Correct.
What can I do with 11 gallons?
We did some research, and we looked up this the World Health Organization. They said that an average human can go roughly on 5 gallons a day. Actually, the basic necessity needs like showering, cooking,
Okay.
in poor and developing countries.
So we need one of these per person or per 2 people? Yeah?
This is
That's something we're basically working on, I guess you could say, about the size. And how many, like, you could get a lot more if you add like multiple lenses. So like it will boil faster, and then you'll have a more efficient
Faster.
system.
right.
So, but as is with one lens, that's more or less what it will get you right now.
Given that your lens is 3 feet across, what do you expect the footprint of this current model to be?
Between 3 and 5 feet max. 5 feet max is what we're looking into.
You mean 5 by 5?
5 foot, 5 no.
5
oh.
cube?
Oh, you said it's 3 feet wide, so I was like.
Well, you said that the lens spec is
Yeah.
36 by 27. So what is your footprint that this is going to sit in?
The whole
The
entire
whole
system.
system.
Yeah.
We're aiming for something relatively small. Basically, the lens would take up as much space as the entire system, I guess you could say. But since it's like higher and it's all focused on one
Right.
point, you can use the space on the side. So we're aiming for something about the size of like one of these tables, more or less.
Okay.
So you know how wide do you need the sunlight on the lens to hit?
Yes.
I mean, it's not a point.
It's not a point. We're not using a focus.
So
It's
it's
about
actually
3 to 5 inches.
3 to 5 inches. So that's why you leave open, and then you can build around
And
that.
then everything else around it would be used.
But I think your main problem is going to be your flow rate of the input of your water, not
Yes.
just increasing another lens and boiling more water,
Yeah.
because your limiting factor is you have no pumps, you're feeding on gravity. So you would need to calculate how much water you're going to be able to get through before you calculate how much lens you
Yeah,
need
Yes,
to
yes,
boil.
yes.
that's one of the.
That's one of the
analysis.
analysis of the steady state.
Okay.
From the first stage, from gravity fed from the filter to the boiler, and then from the unprocessed water reservoir to the boiler. We need to calculate how much water is getting into the boiler itself before we can see how fast we're evaporating the water. So this is a rough estimate of what we could get.
I mean, it could be the fact now that you're still going to have water all the time and there's not enough steam, so and then you would need another one. So you gotta calculate that.
Yes.
And I would do it both ways. You know, you have to do it as respect to the flow rate input as well as the heat production of the lens.
Right.
Make maybe a graph or a table on two of those things.
Right.
I guess my final question, what is your plans as it relates to the design, the prototype and the testing to validate your design? Well, what is your plan with regards to that? The validation of your design via testing or modeling or some kind of strategy like that?
We are going to do both actually. We're going to make like the SolidWorks design and like all the studies in SolidWorks, and then we're actually building and testing this thing throughout the summer most likely.
Also, to add to that, I've seen videos of how the trackers and actuators work in response to how we focus the point, and it can be done. Depending on, I've checked out different materials to be boiled in, so when we're prototyping, we will choose the closest to our ideal goals to make sure.
Let me see your timeline as to how that is addressed. Okay, you do have a testing component.
Yes.
Simulations and testing, I guess.
Yeah.
And then they will compare the results.
And one last thing is on your boiler, keep in mind the color of it.
Yes, the boiler.
Because you have absorption and loss of heat due to
Yes.
the refract,
That's
you know.
one of the reasons why we're still not decided on the material. We said we could use
For
glass.
example, a black color would absorb better the heat,
Yeah.
but it will lose it as well, so you gotta figure that out.
That's, yeah, we're definitely looking into that.
I actually have looked into that. There's high temp conductivity paint you can paint your materials in to make sure you get the best absorption. It's black.